Hello all, welcome to Introduction to Atmospheric Dynamics. In this section, we're continuing our discussion of the analysis of the dynamical equations by considering vertical motion within a fluid column. In particular, we'll be looking at buoyancy and convection of individual fluid parcels. Our focus for this lecture will be on the troposphere. In the troposphere, we notice that temperature varies approximately linearly with height. That is, for every unit distance we go up in height, we drop by a corresponding unit of temperature. This linear temperature profile holds largely through much of the troposphere and consequently is an interesting topic of analysis. By definition, this change of temperature with height is called the lapse rate in the atmosphere. The definition formally of the lapse rate is the rate, in this instance in degrees Kelvin per kilometer, at which temperature decreases with height. Note that the lapse rate automatically includes a negative sign, so that it can be written as gamma equal to negative T Z. This forces the lapse rate to be positive for a decrease of temperature with altitude. The linear decrease of temperature with altitude is related to the conservation of potential temperature following fluid parcels. Namely, for a dry adiabatic stable hydrostatic atmosphere, potential temperature will not vary in the vertical direction. This is related to the fact that following a fluid parcel undergoing adiabatic motion, potential temperature will be conserved. That is, if there's no external heating or cooling applied to the fluid parcel, then potential temperature will be conserved following that fluid parcel. Hence, fluid parcels are free to move up or down through the fluid column while conserving potential temperature. Consequently, for a dry adiabatic stable hydrostatic atmosphere, potential temperature is conserved in the fluid column. So the question then becomes, under the assumption of di theta di z equals 0, how does temperature then vary with altitude? In order to understand this, we can relate temperature to potential temperature using the Poisson relationship shown here at the bottom of the slide. So starting with this initial relationship, we can expand the adiabatic change in temperature with height using the formula above. Then setting di theta di z equal to 0 and relating di t di z to the remaining term in this equation, we observe that for a dry adiabatic hydrostatic atmosphere, the lapse rate, denoted here by gamma d, is going to be given by g over cp. Typical values of g are about 9.8 meters per second squared and cp 1004 joules per kilogram Kelvin. Relating these quantities gives a lapse rate of about 9.8 degrees Kelvin per kilometer. So by definition, the dry adiabatic lapse rate is the rate in Kelvin per kilometer at which the temperature of an air parcel will decrease with height if it's raised adiabatically. This quantity is typically taken to be about 9.8 K per kilometer. So in the troposphere then, we would assume that the rate of decrease with altitude would be approximately equal to this dry adiabatic lapse rate. However, if you examine this figure closely, you'll notice actually that the rate of temperature decrease is slightly lower than that. That is because the troposphere is not perfectly adiabatic and has to deal with, for instance, moisture content, which comes with it condensation and evaporation, which then modifies the associated lapse rate. However, for the considerations of this lecture, we will simply be working with dry fluid parcels. So, even in adiabatic motion with no external sources of heating, if a parcel moves up and down, its temperature will change. This is because the pressure of the external environment changes. Consequently, because the atmosphere is a compressible fluid, we will observe that fluid parcels will expand or contract depending on the temperature of the external environment. So even though potential temperature is conserved, the pressure of the external environment changes, and consequently the temperature of the external environment must also change. So what happens then if a parcel moves around a surface of constant pressure? Well, on a surface of constant pressure, there is no change to the volume of the fluid parcel because it is experiencing constant pressure along its exterior. Consequently, the potential temperature will be conserved and the temperature will be conserved. If the parcel moves about a surface of constant height, the pressure may change for the fluid parcel, and consequently the temperature of the fluid parcel may change. So one needs to be very careful when considering how the parcel movement impacts the temperature of the parcel. If the atmosphere is in adiabatic balance, the temperature will still change with height. Keep in mind that in a compressible atmosphere, pressure varies in the vertical direction, and so even under adiabatic conditions with no external heating, we will still have that temperature changes in response to contraction or expansion of the fluid parcel. This is to emphasize that adiabatic does not mean isothermal. This is often a point of confusion among students of atmospheric dynamics. In fact, adiabatic means no external heating or cooling. It does not mean that the fluid parcel is kept at a constant temperature. Okay. So as mentioned earlier, the change in temperature through the troposphere is given by the vertical lapse rate. In the troposphere, it's not the dry adiabatic lapse rate that governs this linear profile because in general the atmosphere is not dry. If air reaches saturation, so for instance if conditions are right for cloud formation, then condensation will form, and this transition from vapor to liquid phase will end up releasing energy. Consequently, whenever condensation occurs, this will provide a source of heating for the fluid parcel. And so the lapse rate then is reduced for the fluid parcel whenever condensation is present. That is, the condensation provides a mechanism that counteracts the adiabatic cooling that occurs when the fluid parcel reaches lower pressures. Typically, the moist or saturated adiabatic lapse rate is approximately 5 K per kilometer in the troposphere typically. However, the average lapse rate in the troposphere is about 6.5 K per kilometer. That is because the amount of moisture in the atmosphere is usually not sufficient in order to saturate all fluid parcels. So as an average, the fluid parcels will find themselves somewhere between the moist lapse rate and the dry lapse rate. Okay, so let's consider how fluid parcels then behave in an environment where temperature decays roughly linearly with altitude. Consider here a fluid parcel, shown here through the black box. It is put in an environment with warmer temperatures near the surface and cooler temperatures at altitude. Again, the decrease of temperature with altitude is approximately linear. Let's consider how this fluid parcel behaves if it is displaced upward or downward. This method is known as the Parcel method. That is, we're going to consider an arbitrary air parcel sitting in the atmosphere that is displaced up or down. We will then assume that the pressure adjusts instantaneously on the bounds of the fluid parcel. That is, that we assume that the volume of the fluid parcel responds instantaneously to the pressure experienced on the outside of the fluid parcel. As the parcel moves, its temperature will change according to the adiabatic lapse rate. That is, as we're assuming in this case, the fluid parcels are dry and consequently do not have any condensation that can modify the lapse rate from its dry adiabatic value. So as the parcel moves up and down, it will respond instantaneously to the external pressure, modifying the volume and hence modifying the temperature of the fluid parcel. Importantly as well, this will also lead to an adjustment in the density of the fluid parcel, which will then determine its buoyancy in the external environment. So consider what happens if the fluid parcel is displaced upwards and finds itself cooler than the surrounding environment. This figure depicts a cooler fluid parcel that finds itself in a warmer environment. In this case, because the temperature of the fluid parcel is cooler than its surroundings, it will find itself to be heavier than the surrounding environment and so will sink. In this case, the density of the fluid parcel is also less than that of the surrounding environment because of its cooler temperature. If the fluid parcel moves up and finds itself warmer than the environment, then it will have a smaller density than the surrounding environment and consequently will continue to rise. This is an example of instability, for as the fluid parcel continues to rise farther and farther, it will continuously find itself warmer than its surroundings and will continue to rise higher. It will continue to rise then until the potential temperature of the fluid parcel matches that of the surrounding environment. Okay, let's consider this quantitatively. If we assume that temperature is a linear function of height in the background environment, we can write the temperature profile as surface temperature minus environmental lapse rate times altitude. Again here, the environmental lapse rate is defined as negative dt di z. This is analogous to a first-order Taylor expansion of the temperature. So if our fluid parcel is then displaced from an altitude z to a distance z plus delta z, then the change in temperature of the surrounding environment will be given by delta T, which is equal to the temperature of the background environment evaluated at z plus delta z minus the temperature of the background environment evaluated at z. Canceling like terms then simply gives negative gamma times delta z. This is consistent with a finite difference approximation for the environmental lapse rate above. Okay, now let's consider the temperature difference in the fluid parcel and the temperature difference in the surrounding environment. The fluid parcel undergoes dry adiabatic motion, and consequently, its change of temperature with altitude is governed by the dry adiabatic lapse rate. So the change in temperature of a fluid parcel then will be given by negative gamma sub d delta z. The background environment, on the other hand, as we talked about on the previous slide, will be given by negative gamma delta z. Be sure not to confuse the gamma sub d and the gamma. The gamma in this case is the environmental lapse rate, which is arbitrarily specified and simply describes the background environment. The dry adiabatic lapse rate, on the other hand, emerges because the fluid parcel is undergoing dry adiabatic motion. So gamma d in this case always refers to the 9.8 K per kilometer that we discussed earlier for dry adiabatic motion. So under stable conditions, the fluid parcel finds itself cooler than the environment when adjusted upwards. In this case, because the fluid parcel is cooler, it will tend to sink back down and return to its initial position. Since the initial position of the fluid parcel is the same temperature of that of the environment, it must also be the case that the change in the temperature of the parcel as it's adjusted upwards must be smaller than the change in the temperature of the background environment. If we then plug in our delta t's from the previous slide for the fluid parcel and for the environment, we then obtain an expression of negative gamma sub d delta z must be less than negative gamma delta z. Multiplying through by -1 then flips the sign of the inequality, and we can then divide through by delta z on both sides since this is a positive quantity. Consequently, in a stable environment, we conclude that the environmental lapse rate must be less than that of the dry adiabatic lapse rate. In an unstable environment, a fluid parcel that is adjusted upwards will find itself warmer than the surrounding environment and consequently will continue to rise. Since the initial position of the fluid parcel is the same as the temperature of the environment, this again implies that the change in temperature of the fluid parcel must be greater than that of the change in temperature of the surrounding environment. Substituting in our changes in temperature in terms of the corresponding lapse rates then allows us to obtain an expression for an unstable atmospheric environment. We hence conclude that in an unstable atmospheric environment, the lapse rate must satisfy that the environmental lapse rate is greater than the dry adiabatic lapse rate. That is, the temperature in the environment in the unstable case must drop faster with altitude than the dry adiabatic lapse rate. Consequently, we obtain 3 different conditions associated with stability of a background environment. And the environment is considered stable if the dry adiabatic lapse rate is greater than the environmental lapse rate. It's considered neutral if the dry adiabatic lapse rate is the same as the surrounding environment, and it's considered unstable if the dry adiabatic lapse rate is less than the environmental lapse rate. So the important consideration here is that a compressible atmosphere is unstable if temperature decreases with height faster than the adiabatic lapse rate. Note that this is not a condition for an isothermal fluid column. Instead, the linearity, or the degree at which the temperature changes with altitude, determines the stability of the surrounding environment. Okay, returning to the fluid parcel model, let's consider what happens quantitatively. We consider a fluid parcel embedded in an environment that's in hydrostatic balance. That is, the environment has no acceleration associated with it and hence satisfies a hydrostatic balance law equal to the one given here. That is, there is a balance between pressure gradient force in the vertical direction and gravitational force. However, our parcel may experience an acceleration due to buoyancy. The acceleration that it experiences can then be written as the material derivative of the vertical velocity with respect to time. The vertical velocity may also be written as the change in vertical coordinate following the fluid parcel, and hence the dw dt can be written as d squared z over dt squared. The right-hand side here denotes the force balance experienced by the fluid parcel. It also experiences pressure gradient force and gravitational force. However, the difference between the environment and the fluid parcel is that the density of these two may be different than one another. Here we have also assumed that the pressure of the fluid parcel adjusts instantaneously to the environment. So although here we have a separate pressure, P sub P, actually this is going to be the same as the pressure of the surrounding environment, P and env. Hence we can take the hydrostatic balance law from the first line and actually substitute it into this second equation at the bottom. In doing so, we then have an expanded expression for the acceleration experienced by the fluid parcel written in terms of the difference between the density of the environment and the density of the fluid parcel. In particular, we have that the change in vertical velocity following the fluid parcel is given by g times the density of the environment minus the density of the fluid parcel, all divided by the density of the fluid parcel. This makes sense. Namely, if we have a fluid parcel that is more or less dense than the environment, then it'll experience a buoyancy force that leads to it either sinking or rising in the environment. In order to convert these densities to temperatures, we can use the ideal gas law, and in doing so obtain the second equation below on this slide. This second equation then can be used in conjunction with the linear change in temperature that we know for both the environment and fluid parcel for small adjustments from an initial position z0. Namely, we know that the fluid parcel satisfies the dry adiabatic lapse rate, and so as the fluid parcel adjusts from its initial position, the temperature will change in accordance with T at z0 minus gamma sub d z minus z0. That is, at position z equals z0, it'll have the temperature of the reference altitude z0 and will adjust linearly about that reference altitude. The environment, as well, for small displacements is considered to have an environmental lapse rate gamma, and hence a temperature profile which is given by T environment equal T at z0 minus gamma times z minus z0. Again, we emphasize that the fluid parcel and the environment have the same temperature at the reference altitude z0, and we are interested in considering what happens if the fluid parcel undergoes small displacements from that reference altitude. Substituting in these temperature profiles into the equation above then gives an expression for the second derivative of the height coordinate following the fluid parcel. A binomial expansion can be used in order to transfer the denominator into a term which is more amenable to analysis. Substituting in the binomial expansion and considering small displacements, that is, values of z which are close to z0, allows us to ignore the quadratic terms in this expansion and simply obtain an ordinary differential equation describing the altitude of the fluid parcel. If we then define a displacement from the initial position delta z as z minus z0, then this allows us to rewrite the differential equation here in the middle box as below. This is then an ordinary differential equation in delta z. Let's consider the possible solutions to this differential equation. Note that this is a constant coefficient differential equation. That is, we have here assumed that g, t at z0, gamma d, and gamma are all constants. Hence, we can use calculus in order to determine the solutions of this differential equation exactly. Do you recognize the equation and its solutions? There are actually three cases that emerge from this differential equation. We can have that the constant is either greater than 0, equal to 0, or less than 0. These cases actually correspond to the case of stable, neutral, and unstable atmospheres, as we will now see. So in the case of the constant being greater than 0, This corresponds to a stable atmosphere. That's because the solutions of this equation for a positive constant are given by sinusoids, namely sine or cosine functions in time. Consequently, a fluid parcel that is adjusted upwards will tend to oscillate in altitude about the initial location z0. Typical solutions then look like delta z equal delta z0 times sine of Brunt-Väisälä frequency times time plus phase. The Brunt-Väisälä frequency here is a special concept defined for stable atmospheres, and it's the frequency of an oscillating air parcel in a stable atmosphere, defined as n squared equal gamma d minus gamma times gravity divided by the temperature at the reference altitude. So in a stable atmosphere, a fluid parcel that is displaced upwards will find itself cooler than the surrounding environment, hence more dense, and hence will sink in the background environment, returning to its initial position with a small negative velocity that causes it to overshoot that position. As it falls below the initial position, it then finds itself warmer than the surrounding environment, and hence will rise back up, experiencing an acceleration upwards. As it hits its initial position, it has a small positive velocity. Consequently, this pattern will continue and the fluid parcel will oscillate up and down in the background environment. These conditions occur when the environmental lapse rate is smaller than that of the dry adiabatic lapse rate. Consequently, the rising fluid parcel cools more rapidly than the surrounding environment when it's displaced upwards. And so it will always find itself denser if displaced above the initial position, or less dense when displaced below the initial position. The Brunt-Väisälä frequency can be shown to be equivalent to another form in terms of the potential temperature. This form is often more convenient to use. And this is given by n squared equal to g over theta di z. Note that the Brunt-Väisälä frequency is only defined when n squared is positive. As we'll see in the case of an unstable environment, the right-hand side of this expression is actually negative, which would typically give rise to an imaginary Brunt-Väisälä frequency. This is considered unphysical, and hence the Brunt-Väisälä frequency is not used in this case. There are many examples of such oscillations that exist in the real world. One such example pops up in the case of wave clouds. Under certain conditions, you can often look up in the sky and see subsequent bands of clouds that appear to be equally spaced relative to one another. If the air in the upper atmosphere experiences a constant wind and is under stable conditions, we will have oscillations of fluid parcels within this environment as it translates upstream. Consequently, at the top of these oscillations, when the fluid parcel is at its coolest, this is typically where condensation will occur, and hence we will get cloud formation. Hence you have thicker bands of clouds at the top of these oscillations and thinner bands when the fluid parcels are at the bottom of the oscillation in a warmer environment. This is a schematic diagram illustrating the formation of mountain waves, also known as Lee waves. If you have an initial wind field that comes in from the left and moves over topography, that will lead to oscillations within the fluid parcel because of a displacement of the fluid parcel upwards by the associated topography. As the wind continues to blow from the west, these fluid parcels will oscillate up and down. At the peak of the oscillation, you'll get the formation of clouds. Lenticular clouds are an example of the type of clouds that can form under such stable conditions. This is because of airflow over a mountain. Under stable conditions, the air parcels do not rise indefinitely, but instead move smoothly over the mountain. As they reach a sufficient altitude for condensation to form, you get the formation of a cloud-like shape above the mountain. Let's consider the case of neutral conditions. So if the coefficient in front of the delta z is equal to 0, this corresponds to the case of a neutral atmosphere. The differential equation describing delta z then simply reduces to the second material derivative of delta z equal to 0. The solutions of this differential equation are simply constant delta z or linear functions of time. Since the constant delta z case is uninteresting, and because initial conditions require that delta Z be 0 initially, we then have that the fluid parcel, that the relevant solution will be that delta Z is equal to U naught times T. This simply means that in a neutral state, the initial upward velocity experienced by the fluid parcel will remain constant. So the fluid parcel, if given an initial upward velocity in a neutral atmosphere, will continue to rise at a linear rate. Under unstable conditions, the coefficient in front of the delta Z here is negative. The solutions of this differential equation are actually exponentials and include both a growing exponential term and a decaying exponential term. At least one of these solutions will grow without bound. This is associated with a fluid parcel that continuously finds itself warmer than the surrounding environment, and hence will rise indefinitely until it finds itself at a temperature consistent with that of the surrounding environment. In this case, the fluid parcel, when adjusted upwards, is warmer than the environment and less dense. This is where it finds itself in an unstable state and will continue to rise indefinitely. Shortly after the fluid parcel enters into an unstable configuration, it will actually break the constraints imposed here by this quantitative analysis, which initially assumed small perturbations from the initial state. Unstable conditions associated with rising fluid parcels are associated with events such as large-scale convection. This can give rise to cumulonimbus clouds, for instance, and other forms of large storms. Okay, so discussing static stability, we found that the Brunnfeisala frequency can be written in this equivalent form in terms of potential temperature. It is left as an exercise for the reader in order to show that this Brunnfeisala frequency is actually equivalent to the previous form of the Brunnfeisala frequency that we discussed in terms of the difference between the environmental and dry adiabatic lapse rates. However, we can also show that using that difference between environmental and dry adiabatic lapse rates, the conditions for stable, neutral, and unstable atmosphere have equivalent forms in terms of the vertical change in the potential temperature. In the environmental state, if the potential temperature increases with altitude, this condition is known as statically stable. If the potential temperature is constant with altitude, this is statically neutral. And if the potential temperature decreases with altitude, then this state is known as statically unstable. This makes sense because a rising fluid parcel that undergoes dry adiabatic motion conserves its potential temperature. So if that fluid parcel rises in a statically stable atmosphere, the potential temperature of the fluid parcel will then be less than that of the surrounding environment. Or equivalently, the temperature of that fluid parcel will be less than that of the surrounding environment because the pressure is consistent in each case. In the case of a statically unstable atmosphere, a rising fluid parcel will again retain its potential temperature, and that potential temperature will be larger than that of the surrounding environment. Consequently, the temperature of that fluid parcel will also be larger than that of the environment, and so the fluid parcel will continue to rise. So there are two ways in order to determine stability of the environment then. If the environmental lapse rate is less than the dry adiabatic lapse rate, this is equivalent to the change in potential temperature with height being greater than 0. If the environmental lapse rate equals the dry adiabatic lapse rate, then this is the same as the potential temperature change with altitude being 0 and corresponds to a statically neutral atmosphere. If the environmental lapse rate is greater than the dry adiabatic lapse rate, this corresponds to a decreasing potential temperature with altitude and corresponds to a statically unstable environment.